In Arizona, just about every house has a pool because it's so hot here all the time. So one of the key things you have to do is teach your kids to swim. And I've found that you reach different milestones in swimming, but the toughest one is to go from the floaty thing down to nothing, to where they're just in the pool. So your child will be standing on the edge. You're like, come on, honey, jump in, and no, I'm scared. And you're like, no, it'll be fine. I'm right here. Just jump in. No, I'm scared. You just got to reach the point where you get out of the pool, pick up the child, and chuck him in. No, hey, wait. Before you call CPS, you go in with them, right? And you help them, and they just got to tread water a little while, and then they get it, and they're like, oh, okay, this is kind of fun, and you help them around the pool and all that kind of. So subnetting is the same way. I have found through many years of teaching, rather than start off with, okay, well, here's the I mean, you just got to jump in. You got to say, okay, here's the situation that requires subnetting. Let's do it. So in this opening IP subnetting nugget, I'm going to show you how to subnet based on network requirements. So here is the situation. Here is something that would require custom subnetting. This organization has purchased the Class C address 216.21.50. Now, stop right there. What do you mean purchased? Why do I need to buy IP addresses? Well, keep in mind that when we're working with IP addresses, there are private IP addresses and there are public IP addresses. The private one you don't have to pay for. They are available to you. You can create them, make them up, whatever you want inside of your own network. I believe we've talked about them already. They are anything that start with the number 10. They are anything with 172.16 through 31.255.255, if you will, /16, or they are 192.168. anything /16. So essentially, if the first two octets are this, or the first octet is that, it is a private address, as in they're yours. You can create them, make them up, design your own internal networks all day, but those IP addresses don't work on the internet. They are blocked by every single service provider that are out there. So public addresses are anything that is a valid address outside of those ranges. For example, this one. So this organization has purchased a block of public addresses that they want to use inside of their organization. They want all of the devices inside of their organization to be directly on the internet without the use of NAT or any technology like that. Now, is that normal? I've seen it before, but it's not a normal thing, but it works really well for a subnetting scenario. So that's the situation that we've found ourselves in. So the organization has purchased a Class C address that is this block. So that means they can't go outside of that. Now, when you purchase a Class C address, 216.21.5.0 with a Class C subnet mask 255.255.255.0, how many networks do you get? One, right? 216.21.5. How many hosts do you get? Well, 256 IP addresses total here. 254 that are usable because you can't use 0 and you can't use 255. So everything in that squishy Oreo center is usable on the host side. But here's the problem. Let's look at this situation, because it says the organization has purchased this and would like to use it to address this network. So we look at this. Now let me ask you the question. How many networks do you see in this picture? Pause the nugget. Think about it. I see 5. 1, 2, 3, 4, 5. Essentially, every interface of a router represents the end of a network and the beginning of a new. So if I connect another interface here to another group of computers, that would be 6. There would be another network that would be represented there in that picture. So every interface of a router divides up a network. And think about it. That's what a router's lifeblood is. It's to divide networks, to stop broadcasts. Like a broadcast that happens here on this network stays on this network because that's all internal right there. The router will not let that pass. You shall not pass. So we look at this and we go, okay, well, this poses a problem. We have our organization which has 5 networks, right? But we've purchased a Class C address that only gives us one network, 216.21.5. Enter subnetting. Subnetting, or the full word, subnetworking, is taking your one network and dividing it up into many. Now, if I were to break it down even further, I would say it's sacrificing how many hosts you can have per network to get more networks. So essentially, we move this bar over a little bit more so that maybe half of that 0, if you will, represents the network side, and half of it represents the host. Now, looking at it in a decimal sense, it's crazy. You can't just draw a line through a 0 like that. But when you break it out in binary and you go, oh, well, there's actually 8 bits. Actually, they're all zeros. And that's really 8. There's 8 bits that represent that 0. We could move the line over and maybe put a line in there somewhere that divide these 3 bits go to the network side, these 3 bits go to the host. That's what subnetting is. So here's the process. 3 steps every single time. 1, determine the number of networks that you need and convert it to binary. 2, reserve the bits in the subnet mask and find your increment. And 3, use the increment to find your network ranges. Now, at this point, those 3 steps don't mean anything because we haven't gone through them, so let's start treading some water. This was the network that we were given, 216.21.5.0. That's what we purchased from our internet service provider that we're going to subnet for our whole organization. So step 1 is to determine the number of networks and convert it to binary. Well, that's an easy step. We determined on the last slide that there are going to be 5 total networks. Remember, every single one of those router interfaces represented a network that they were connected to. So 5 networks, and we need to convert it to a binary number. Enter Rico skills from the last nugget. 128, 64, 32, 16, 8, 4, 2, 1 is our values that we're going to use for subnetting, our binary values. So no, 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 yes, no, yes. So 5 really represents 0, 0, 0, 0, 0, 1, 0, 1 in the binary realm. That's it. That's the whole first step. So, second step, reserve bits in the subnet mask and find your increment. Well, what does that mean? Well, the way that we do this is to take that subnet mask and look at it the way our network devices look at it, in binary. So now you're going to want to shortcut this at the beginning. Don't do it at the beginning. I'll show you some shortcuts later. But while you're first starting in this, you want to write that subnet mask in all binary. It's not as hard as it sounds, right? 255.255.255.0. What is that as a binary number? What is 255? All 8s. Or wait, all 8s? Totally wrong. No, all 1s. It's 8 ones. 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Dot. So I'm just converting that whole thing to binary. And then what's 0 in all binary? Really easy, right? 0, 0, 0, 0. 0, 0, 0, 0. So that is what it looks like in all binary. Okay, so what does it mean to reserve bits in the subnet mask? Okay, well, we have to look at this. We say determine the number of networks. Now, I'm looking right here. Okay, 5 networks. Now, let me ask you a question. It's a little tricky the first time you hear it. How many bits did it take to get the number 5? 3. 3 bits. Now, it's really common. Some of you probably did this, to look at this and say, oh, well, 2 bits because I only see 2 ones. Well, you're thinking about it a little off. If you're thinking 2 bits, that's what it would mean, just those 2 bits. What's the biggest number you could get with 2 bits? 3, right? 1 plus 2 would be 3. So we look at this and we go, okay, well, it's actually 3 bits. I can't get the number 5 with any less than 3 bits. Right? So now I need you to take another mental leap with me. Previously, in everything that we've been talking about, we've said 255 represents the network. 0 represents the host, right? When we're lining up the subnet mask to the IP address, that's how we find our network and host. So I need you to take a mental jump with me. Is it okay to make this statement? 1s represent the network and 0s represent the host. So is that an okay statement? Yes, okay, good. So we've got 1s representing the network. Okay, let's start putting some of these pieces together. So I can't get the number 5. I can't, and let me put a little more to this. It's like I'm unpacking this as we go. So I can't get the number 5 with any less than 3 bits. And I've just made the statement that network bits really are 1. So what does it mean when I say reserve bits in the subnet mask? Here's what it means. It means I pick up right where the 1s leave off, and I say I need 1, 2, 3 network bits. The rest of these can stay host. I can't get 5 networks with any less than 3 bits, so I'm going to add 3 more network bits onto there. Now, whoa, stop the train. Big statement right there. Wait a sec, Jeremy. I thought this was 101. Why did you put 111 there? Well, it doesn't really matter at all what the binary number is up here. At all. What we're after is how many bits does it take to get that binary number. If I had the number 20, I would look up here and I go, okay, well 20 is 0, 0, 0, 1, 0, 1, 0, 0. I don't really care that it's 1, 0, 1. I just know that it takes 5 bits to get the number 20. That's what I'm after. I'm not really after the binary number at all. I'm just after how many bits. So when I come down here, I can say, okay, well, as I'm looking at my subnet mask, I need 5 networks, so I need to extend that subnet mask by 3 network bits to make that possible. Okay, so believe it or not, at this point, we already know what our subnet mask is going to be for this entire network. How? Well, we can take this and convert it back to a decimal number. Pretty straightforward. 255.255.255, because these first 3 haven't changed, and frankly they can't change because that's what we were given. We can only subnet the host bits because that's our playground. The zeros are where we can kind of make modifications. This is what the service provider gave us. That's what we bought, so we can't change that. So what is this last one? Well, that's where we have to use our binary to decimal skills. I have to take this and convert it back to a decimal number. So let's line it up. 1, 2, 3, 1, 2, 3, 4, 5. So I really have to take 128 plus 64 plus 32. Carry the 1, minus 2, 224. Yeah, trust me, you'll start getting used to some of the common values that you're going to see. And it's the beauty of subnetting. There's only 8 numbers that you're really going to run into. So our new subnet mask becomes 255.255.254. Every router will have that. Every computer will have that subnet mask in that network that we just saw in the last slide, that picture. Everything will use that subnet mask. And you can be like, yeah, doing the dance. I got the subnet mask we're going to use for the whole network. That's great, but it doesn't mean a thing to us yet. It's just a number. It's like, well, there it is. That's the right answer. Choose C, if you will. But I don't know what that means yet. Well, that's the second half of this. We reserve the bits in the subnet mask and find your increment. What is the increment? So we did the reservation. So the increment is actually the lowest network bit converted back to a decimal number. So let's think about it. This is 128, 64, 32. The lowest network bit, essentially where the ones end and the zeros begin, the lowest network bit converted back to a decimal number represents our increment. Oh, okay, so it's still another one of those right answer things, like I got the subnet mask, I got the increment, I have no idea what it means yet. Well, the last step is to use that increment to find your network ranges. Okay, this is where it all gets put together. 32 is our increment. This is what we were given, and we can start using that increment to find out how many IP addresses I get per network. The way I do that is simple math. 216.21.5.0 is where I start, and then I just start adding that increment in whatever octet, whatever position that it's located. It's in the 4th octet, so I go, okay, the next one is 216.21.5.32. 0 plus 32 is 32. 216.21.5.64.96.128. I'm just adding 32. It just keeps going down all the way. Filling those in, and you can keep that going down all the way as well. What is that? That is the starting position for each network. 216.21.5.0 is where network 1 begins, and it goes through. Now we can go back. Once we just go down, we can go back and fill in the last IP address. 216.21.5. What's one less than 32? I know some of you are like, is it really that simple? Yeah, it's not tricky. 31, right? 216.21.5.63. That's the last IP address before 60. So I'm filling in the last one just by looking at where the next one starts, and I go, okay, -1, then that must be that fills in. So this goes to 216.21.5.95 and this we just keep subtracting 1, but now it's become real. Let me show you. I come back here to my network situation and I realized I needed 5 networks. So now I can start assigning them. This is actually going to be 216, no, network 1, 216.21.5.0 through 31 with a 255.255.255.224 subnet mask. I won't write that every time, but here's the subnet mask, here's the range. So I will assign the devices in that network IP addresses in this range, 0 through 31. So I would probably assign the router, the first one. So the router would get 216.21.5.1, and then maybe a DHCP scope for the rest of them. Maybe this computer's .2 and the next computer's .3 and all that kind of stuff. So they actually get, as long as I don't exceed 31. Now keep in mind. Whoa, wait a sec. Stop the train. Remember, when we're doing IP networking, we can never use the first address or the last address. Why? The first one represents the network, and the last one represents the broadcast. So I can't actually assign something 216.21.5.0 because that identifies the whole network. It's an identifier. It's not valid. Same thing, I can't assign someone 216.21.5.31 because that's a broadcast. If I wanted to send a message to everybody on that network, I would send it to that IP address, to the .31, and everybody would get it. It's a broadcast address. So we can't assign that. So usable, we actually get 1 through 30 for that range. So that's network 1. So that's number 1 right there. Number 2 is this guy, 216.21.5.32 through 63. So it would come back here and say, okay, you are 216.21.5.32 through, what did I say, 63? 63. But realizing I can't give 32 or 63 to an actual device, so because that's the network, that's the broadcast. So usable, I actually get 33 through 62. So maybe the router gets 216.21.5.33. That's everybody's default gateway. That's how they get off of their network, is going to that 33 address. And then this guy maybe is .34, and his friend is .35. And all the other devices that are on that network get IP addresses that are in there, as long as I don't assign something to that. So what I've done, take a moment. Let's look at the concept. I've taken the one network and broken it down to where I can address all of the networks in this situation. Now, let's fill in some questions. Now, some of you mathematicians out there are looking and going, wait a second, this is going to give me more than 5. I can see that. It's 1, 2, 3, 4, 5, and then, this goes higher, right? It does. It's going to give you more than 5 because of how the binary works out. That's just, if you look at it, you only have 8 numbers that it could be. So it's going to be something in that range. So the way to think of it is this scheme will give you at least the 5 networks that you asked for. Okay. So next question then becomes, well, how do I know how many networks it'll give me? Or for that matter, how do I know how many hosts I can actually have on the network? Well, there's a simple formula. I say simple if you have a calculator, but simple to where you can type in 2 to the power of however many bits you would like to put in there and find that question out. So let's do it this way. Let's say you're asking the question, well, how many networks does this give me? Well, the way you can find it out is to look at how many subnet bits you ended up adding. So 2 to the power of 3 in this case, because I added 3 subnet bits. So 2 to the power of 3 will tell you how many networks you get. Now, now 2 to the power of 3, it's a little simple because you go, okay, 2 times 2 is 4, and then 2 times, essentially 2 times 2 times 2 is 8. If you're doing it in your head, it's like, okay, I can do that kind of math, but when you get into the larger numbers, it gets really tough. So if you don't have a calculator. So that's why I showed you in the last nugget, these are all the powers of 2. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, 2 to the power of 3 is 8. As long as you remember that it counts from 0, you should be fine just to go, okay, well, the 2 to the power of 3 is right here, so that's 8. So you can do that. So that way, when you get to these larger numbers, you don't have to sit with a piece of paper going 2 times 2 times 2. You can just look right here and go, okay, 2 to the power of 7 is actually 128. See what I mean? So 2 to the power of 3 tells you, with this scheme, if I work this all the way down, I will have a total of 8 networks. Or 8 subnets that I created with this scheme. Or if I want to say, well, how many hosts do I get per network? Well, same formula. 2 to the power of, in this case, we're looking at host bits. That's 1, 2, 3, 4, 5. So 5, there's 5 zeros left over, equals, looking up here, is 32, right? But you have to remember, whenever you're doing the number of hosts, to always subtract 2. Why do you think that is? You remember, right? Can't use the first one, can't use the last one, so those don't count. So we'll say usable hosts end up being 30 hosts per network, right? You have just done your first subnetting question. Now, this is you grab the child and you throw them in the water, right? They're going, water's splashing everywhere. That's the kind of feeling that I have right now as you're going, whoa, it's kind of like I caught a little piece. I'm treading a little water, little bits here and there, but oh man. So let's do another one. For this one, I'm going to skip the picture because it just gets too big to draw. But in this scenario, we've got a Class C network, 195.520, and we want to break that into 50 networks. Okay, now hang on, let's get some bearing here. That means that we've got one network, 195.5.20.0, with a Class C subnet mask, 255.255.255.0. And we want to take this one network, because this typically gives us one network, which is 195.5.20, and break it into 50 different subnetworks. It's a question, is that even possible? Can we do that? Well, let's try it. So first off, step number 1 is to determine the number of networks and convert to binary. So we need 50 subnets. All right. Get our old standby binary chart up here. 128, 64, 32, 16, 8, 4, 2, 1. So 50 as a binary number. So I'm going to go 0, 0, 1. Let me finish this and then I'll give you my shortcut. 50 minus 32. That would be 5, 4, 8, 1. 18 left, right? 1. That'd be 16. That'd be 2 left. So 0, 0, 2, 0. 0, 0, 1 on the 2, 0. And there's a binary number. So 0, 0, 1, 1, 0, 0, 1, 0. Okay. Step 1, check. We got it. Now, step 2, reserve bits in the subnet mask and find your increment. Again, don't skip it at this point. It's going to take a little bit of time, but we're going to write the Class C subnet mask on there in all binary. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so here's where I want to show you a little shortcut. So the statement says reserve bits in the subnet mask and find your increment. So we have to ask the question, how many bits did it take to get the number 50? And I would submit to you 6 bits. Because I can't get the number 50 with any less than 6 bits. Okay, enter shortcut number 1 here. One of the things we're always trying to do is do things a little bit faster. Especially when we're talking about certification exams and time is on the line, all that. You want to try and do things as fast as possible. When you're finding the binary number right here, where it says determine the number of networks and convert to binary, excuse me, when you're finding that binary number, as soon as you put the first 1 on the drawing board, do you know how many bits it's going to take to get that number? Yeah, right? So as soon as I know my first one goes at the 32, I don't have to spend time figuring out the rest of this, because I know no matter what the rest of this is, I don't really care what the rest of it is. I just care that it takes 6 bits to get 50 networks, right? So that can save you a little bit of time there. Okay, so now we're going to do step 2, which is reserve the bits in the subnet mask. Now are we after, here's my question, next question for you. Are we after 50 networks? Or are we after 50 hosts on our networks? Well, the answer is 50 networks. You're looking at, well, Jeremy, that's what the question said, 50 networks, right? Well, yes, and I'm going to keep asking you this question. And the reason why is because later on in the next nugget, we're going to change that question a little bit to the hosts per network. But for now, 50 networks. So I go, okay, I need, that means then I need 6 network bits, right? And we know that 1s are network bits. So I'm going to go 1, 2, 3, 4, 5, 6. Doesn't matter what these were. It doesn't matter. I need 6 network bits because I can't get 50 networks. I can get 50 subnets with any less than 6 bits. Okay, 0, 0 is left over. Not much for the host, right? So that gives us what our new subnet mask is. In decimal form, we know the subnet mask for the network will be 255.255.255. Now, what is this in decimal? Well, two approaches you could take. You could add 128, 64, 32, 16, 8, 4 all together, right? And you could get that number. Or if these are all 1, we know that they're 255, right? So in this case, it would be a lot easier to figure out what we don't have. We don't have a 2 and we don't have a 1, right? So we could either add all these numbers up and get the answer, or we could take 255 minus 3, which gives us 252. Forgive me, I'm starting to throw little shortcuts in here as we go, just to go a little faster. 252, but if the shortcuts don't work for you, add them up, definitely. It's much better to take a little more time adding and get the right answer than go, oh, how was that again? So 252 is our subnet mask. Now, let me add yet another piece. I add these little pieces as we go through this to enhance what you know. Now, we've been talking all along, we've been saying, I think I showed you in an earlier nuggets, like a /24 really equals 255.255.255.0, right? That's kind of a shorthand that's called CIDR notation and all that. And I said like /8 equals 255.000, all those kind of things. Now we can actually see why. This CIDR notation is really just the number of ones in the subnet mask. So when I look at a class C subnet mask, I can say, well, that's 255.255.255.0, or I can say, well, that's 8 ones, 8 ones, 8 ones. Well, that's 24 ones. Thus, /24 is a shortcut way of writing that. You see why it's kind of cool. Once you know the binary, you're like, oh, that's where they get that from. So, a class A address only has 8 bits in that, so it becomes a /8. So the reason I say that is I want to start writing these. Now, this is we started with a /24 here, but I want to start writing these in both decimal and CIDR notation because you're going to see examples of both in the real world and on the exam. This 255.255.255.252 is actually the original 24 bits plus 6 more that I added there, right? That would be a /30. That would be representative of that subnet mask. So again, we're just talking about ways of writing the subnet mask. I can write it this way, or I can write it that way. They both mean the same thing. So okay, let's catch back up where we were. We determined we needed 50 networks. That's what the question gave us. We determined it was 6 bits, so we reserved our 6 bits. So now we know what our subnet mask is going to be for this whole network. So now we need to find our increment. So I'm going to come in here and I'm going to say the lowest network bit, the last network bit, converted back to a decimal number is a 4. That is my increment. So I can come in here and say, I'm going to use that increment to find my network ranges 195.5.20.0 and just start adding 4 to the last octet because that's where the increment is. So 195.5.20.4.20, just going faster, .20, .12, .20, you see where this is going, .16, down, down, and down we go. So that's the start of every single network that I would need for this organization. So what's the end? Well, just subtract 1, 3, subtract 1, 7, subtract 1, 11. So these are actually going, now I'm writing this shorthand, it's actually 195.5.20.0 through 195.5.20.3 through, you see what I mean? So I'm just writing them shorthand. Now keep in mind, we know that we cannot use the last IP address or the first IP address. So what is our usable 1 through 2? What is our usable 5 through 6? We actually have 2, count them, 1, 2 usable hosts per network. And if you think about it, if we're taking a class C and breaking it into at least 50 subnets, well, good grief, we have to give somewhere. Now you might be sitting there scratching your head going, okay, this is just getting absurd. Where would we use a subnet mask that only has 2 hosts per network? Well, believe it or not, you just found the second most common subnet mask in the world. The most common subnet mask is a /24. The second most common subnet mask is a /30 because it's used all over the place when you have WAN links. Oh man, what a perfect fit. So if you have router 1 connected to a network up here, that you got your computers humming along up there. Router 2 is connected to a network down here, and then you've got a WAN link in the middle managed by AT&T or whatever service provider you're using to connect we'll say the Arizona office to the Texas office to connect these two sites. Well, this is a network. And I don't want to waste IP addresses on that network because I know I'll only have how many? 2 devices on that network. One here on this side, that's that router, and one here. This is such a custom fit for this kind of environment because I can say, okay, well, this will be the 192.5.20.0 network /30 subnet mask. So you will actually be .1 and you will be .2, the 2 usable IP addresses. And then all of a sudden, Texas has a need to have a link to the new Michigan office, router 3. Right here, we've got another network. Have a network down here. Now, of course, we wouldn't use this kind of subnet mask on a network down here because you would only be able to have 2 devices in that network. That would be absurd. You're right. But for the WAN link going between Texas and Michigan, sure, let's make that guy 192.5.20.4/30. Again, remember, this represents the network. So when I'm writing documentation, I'm diagramming. I'm saying, oh, yeah, it's the .4 network /30. So he'll be .5 IP address. He'll be .6. Okay, so how's it feeling? Are you getting a little water treading going on, or your head's above water? You're like, okay, I saw what you did. Some of the pieces are starting to make sense. It makes sense. Let's do another one. Hopefully that's the feeling you're getting. So what I'm going to do is change it to where we're moving beyond Class C only examples, to where we're going to start with a Class B address. Now you remember, the Class B addresses by default are /16 or 255.255.0.0. So only the first 2 octets represent the network now. So let's start there and see where that leads us. So number 1. Okay, so let's look at our situation first. We have a Class B network, 150.5.0.0. And we want to break that into 100, count 100 individual subnets or 100 individual networks to disperse around our organization. Okay, so with that in place, let's start off. Determine the number of networks and convert to binary. Well, it was given to us. We needed 100 networks. So let's bring up our binary chart, 64, 32, 16, 8, 4, 2, 1. All right, so 100, let's use our shortcut. Our first one goes right there, right? So from the last example we did, we know we can stop because we know that 100 takes 7 bits. Now again, if that throws you off, then continue on. I think is that 100? 64 plus 32, that'd be 96, right? Yeah, that should be 100. So you could figure out the whole binary value, but still it would still be 7 bits that we get by the time it's said and done. So we're after the number of bits because we need them in step 2. Reserve bits in the subnet mask and find your increment. Now our subnet mask, and this is why it's so, you might be like, well, I'm kind of tired of writing 1s and 0s. It's so super critical that you do, especially when you get to the non-Class C examples, because you want to see where you're at. So 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 dot 1, 2, 3, 4, 5, 6, 7, 8 1, 2, 3, 4, 5, 6, 7, 8. Good. So that's our subnet mask in all binary for a Class B subnet mask. That's where we started with this. So we have 150.5 that we're working with. So I'm looking. I can't get 100 networks with any less than 7 bits. And I remember that I'm after networks. I'm not after hosts per network. So those are the ones. I need more ones. How many of them? 7 of them. Now I'm going to start where the ones leave off. 1, 2, 3. Hang on. I can't do that. I need another color. 1, 2, 3, 4, 5, 6, 7, 0. 1, 2, 3, 4, 5, 6, 7, 8. I'm super visual. Everything I do is I have to draw it. I have to write it. It's funny. I'm such a visual learner. It's to the point of handicap, to where when somebody talks to me, if their sentences go beyond like 3 sentences, if it's a network situation, I'm like, let's go to a whiteboard. I have a 2,000 square foot office that I work in when I'm not working out of my home. I literally have 9 whiteboards put up around the office. Like every room has at least 2 whiteboards on the wall. Like some people put up art, I put up whiteboards because I have to do that. So forgive me when I'm like, I need color, I need something new. So I've reserved my 7 bits. Now, be careful. It's so easy when you're doing this to think in a class C. So you might have your, a bunch of ones, and then you got 1, 2, 3, 4, 5, dot 1, 2, 3, 4. So right here, sometimes people mistakenly start in the last octet, because they're so used to class C examples, like they would start putting ones right there instead of where the ones leave off. Always pick up where the ones leave off. You don't want to have ones here and nothing there. It just doesn't work that way. So at this point, we know what our subnet mask is going to be. It's now 255.255. I'm looking at that third octet now. Now again, you can add all these numbers up. 128, 64, 32. Or you can just remember that it's 255 and I don't have a 1. So that would be 254.0 is our subnet mask. CIDR notation, originally we had a /16, and now we graduated ourselves to a /23 because we added 7 bits onto our 16 right here. So that's our new subnet mask in CIDR. That's our new subnet mask in decimal notation. What's our increment? Another place where a mistake could easily be caused by kind of logically thinking. You're thinking, okay, my increments are 1, 2, 3, 4. Not 1, 2, 3, 1, 2, 4, 8, 16. You start counting, and you're like, okay, 128. So this must be. You see what I'm saying? 256. No, that's not the way to think about it. Don't count from far right. Every octet is a new set of increments, right? So you've got 1, 2, 4, 8, 16, 32, 64, 128 here. Then we start over. 1, 2, 2, 4, 8, and so on and so forth. So our increment is a 2, right? The lowest network bit converted back to a decimal number. Good. Okay, so now, so it's working out. I mean, I'm just kind of showing you the little pieces here and there where you could trip up, but it's the same exact thing as it was previously. So now let's write our network ranges. So we've got 150.5.0.0 because that's what we were given. Now be careful. I need to add my increment, add my 2 in the octet where it's at. Now, I'm not working in this octet. I'm working in this octet, the third octet. So that's where my 2 gets added. 150.5.2.0. 150.5.4.0. You see what I'm saying? 150.5.6.0. And down and down and down and we go down the list. Good? Good. Okay. Last place where you could easily trip up in something like this is to look at it and go, okay, this is going to go through, so my range, the usable addresses are going to go through 150.5. Okay, subtract 1, right? So .1.0. Ooh, that's actually not right. Well, why not, Jeremy? What's wrong with that? Well, my question is, if this one ends at 150.5.1.0, and this one starts at 150.5.2.0. So this is right. This is the end. This is the begin of the next range, right? Are you following? Where does 150.5.1.50 fit? Well, you're like, well, it's in the first. No, I'm sorry. Our range ended at 0 there. That 50 is greater than 0, and you go, well, it's over here. No, that started at 2. So where's that guy fit? Or where's 150.1. Well, anything. 150.5.1.200 fit. Where does that fit? It doesn't. We left them out in the cold. So we have to go back and we have to revise our numbers. Let me just wipe these guys off. Revise our numbers here to say no. Let's get you out. This actually ends at 150.5.1.255. That's the actual last. Like, think of it as some bizarro math problem. Remember when you're first learning math and they go, okay, 19. What happens if I add 1 to that? And I mean, you got to reduce yourself back to an elementary mindset, right? You're kind of like, ooh, well, I can't have 10 there because I can only have 1 digit, so I have to kind of zero it out and carry the 1, if you will, right? So we're in 20. So think of it in like bizarro math world, right? You know that 255 is like your 9 because you can't have any more than that with 8 bits. So if we add 1 to that, what happens? Well, we can't have 256. It doesn't. That value doesn't exist with 8 bits. So it kind of zeroes out and carries the 1. So you're down to 2 here, right? So if that works for you, great. If not, then forget I ever said it. So that's going to follow that same trend the whole way down. This goes through 150.5.3.255. Sweet. Through 150, you see how this is working? 5.5.255. Whew, down and down and down we go. Come on, you got to be looking right now and going, okay, I'm feeling it. I'm seeing how these pieces are starting to fit into place, right? If not, I would say stop here, rewind, go back through it a few more times because like at this point, I would suggest it would be soaking in to where you're like, okay, I'm starting to see how this. I don't know why these weird things like this horse rides or this, like, you know what I mean? Like I'm starting to see the feel of it. Okay, now let me throw something else at you. I'm like, okay, you think you got it? Well, let me show you something. So somewhere in the middle of this range, right, you're going to run into the IP address 150.5.0.255, right? Somewhere in the middle there. You're also going to run into the IP address 150.5.1.0. That's right next to that guy, right kind of in the middle of that range. So again, let's put this back in the terms of a network situation. We've got computers connected to a router. I mean, this company needed 100 networks, so maybe it's something like this, where they've got corporate headquarters, and they've got all these kind of networks over there and computers and all that, and that corporate headquarters goes to all these branch offices. Like let's identify. Maybe it's like a Wells Fargo bank or State Farm Insurance. I'm just throwing companies out there that I would assume would follow this model to where they have kind of a corporate headquarters and then all these little branch offices, strip mall, ATM machines. I mean, it's funny when you know how when you get a car. Like you're driving a new car and you're looking around, you're like, hey, I see like so many of this car on the road, and it's not that there's any more. It's just now that you have that car, you see it everywhere. It's the same thing. When you start getting into the network world, you'll be walking in a store and you're like, I wonder how they do the network for this. I wonder, like, I walk in Walmart, I don't see stuff on the shelf anymore. It's like the Matrix. I just see binary ones. I'm like, how does Walmart? I see a guy with a hand scanner. I'm like, ooh, that's connected to a Wi-Fi network. I wonder how they design. Like that's the kind of thoughts you have. So this is Walmart, right? And this is store 1, store 2, store 3, all that kind of stuff. So all these different stores. So you're like, Jeremy, come back to us. I'm back. Okay. So this network 1 gets assigned to store 1. Right? So can I go to this computer at that store or that hand scanner or whatever device that is and give it the IP address 150.5.0.255? Can I assign this IP address to that computer? Did you get it? Yes, you can. Now, somebody like, no, but no, it's 255. You can't use 255. Isn't that the broadcast? No. Once we've gone beyond a Class C example, we've come into a world where we're kind of moving between big ranges, if you will, to where there's only one network, and that's 150.5.0.0, and there's only one broadcast on this network, 150.5.1.255. Everything in the middle is fair game. So yes, this is a valid address. Yes, this is a valid address. You can't, now it's going to feel really weird. You're going to be like, this ain't going to work. I can feel it now. It's not going to work. It'll work. It'll work as long as you give it this subnet mask, because that tells the computer exactly what the range is. So, I mean, same thing down here. You would run into, in this range, right here, you'd run into 150.5.4.255, somewhere in there. Does it work? Can I assign that to a device? Yes, you can. And it will work. That's the power that we have with these ranges. So already, I know some of you are real world, some of you are really heavy focused on the certification exam. If you're certification focused, already be thinking of a test question. Based on this IP address and based on this subnet mask, which of the following are valid addresses? And I guarantee you those guys are going to show up in the list and be like, oh, no, those aren't valid. Oh, yes, they are. Depending on the subnet mask that you use, they definitely can be valid. Okay, one last example. This one, a Class A example. We've got the 10 network, 10.0.0.0, and we need 1,000 networks. Now, you remember Class A subnet mask is a /8 or 255.0.0.0. And we need to break that into a whole big number of networks. Is that even possible? Well, let's find out. First off, we need to determine the number of networks and convert it to binary. So I'm going to take 1,000 subnets equals, okay, wait a sec. We've gone outside of our 128.64 world are 8 bits, 32, 16, 8, 4, 2, 1, because we know the biggest number that we can get with this is 255. So, can we do it? Yeah, we just need to stretch a little bit more. So I'm going to go to the next increment, 256. If I multiply, powers of 2, 2 to the power of 8 is 256, or 128 times 2. Then we multiply that by 2. That'd be 512. Okay, is that big enough? Well, let's multiply that by 2, and we go, okay, 1024. Okay, well, we've exceeded 1,000 networks. So I know my 1 can't go right here. That's not possible because I can't subtract 1,024 from 1,000. So my first 1 goes right there. Now again, you can figure out the entire binary number for 1,000, but I would say, especially in a number this big, it makes it a lot faster to just say, okay, well, how many bits did it take to get the number 1,000? Well, we had our 8, 9, 10. 1,000 is 10 bits. All right. So, reserve bits in the mask and find the increment. Our original subnet mask, because it was class A, is 255,000. In binary, it looks like this. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Now remember, all these zeros are ours. It's our playground to work with. I got too many there? Yeah. One too many. There we go. So we've got our subnet mask in all binary. Now we go back to the question. What do we need? 1,000 hosts per network or 1,000 networks? Well, in this case, 1,000 networks. We know that to get the number 1,000, it's 10 bits. And we know that network bits are ones, not zeros in the binary scheme of things. So we pick up right where the ones leave off, and we say 1, 2, 3, 4, 5, 6, 7, 8. Oh, I didn't line them up exactly, but that's 8. It lines up to the 8. Dot 9, 10. Because we needed 10 bits to get the number 1,000. I can't do this with any less than 10, so we actually cross the dotted line, if you will, into that. The rest of these can stay 0. That's our new subnet mask. So we've added 10 network bits, so our new subnet mask goes 255, 255, dot, let's see, what's this one? 128 plus 64, since we have kind of those two lit up in this octet. So that would be 192. Dot 0. So that's the decimal version. Or we're moving from a /8 up here down to a slash, that'd be /8, /16, the first two, 17, 18, because we added 2 in that last one. So we're going to a /18 subnet mask. Good. So now the question, what is our increment? Well, our increment is right here. Lowest network bit back in binary. Again, nothing funky. Every single octet restarts the increment. So that's a 64. Like that. And now we just start adding that increment to find our network ranges. So I'm going to start with class A. Let's see, where do I begin? 10.0.0.0 with what we were given. 10.0.0. Okay, what octet is our increment in? This one, the third one over, right? So I'm going to go 10.0.64.0. Whoa. 10.0.128.0. I'm adding 64 in that third octet. 10.0.192.0. And down we go. Now I'm actually going to come back to my down and down and down statement in just a moment. But let me fill in the end ranges first. So this one's going to go through 10.0. Now remember from the last one, this little trick, 63. What? 255. This one goes through 10.0.127.255. We can't cut off that end range, so we're just like the last one. We're going through that, and we would continue this way all the way down. This goes through 191.255. Again, just the last two octets that I'm putting right here. Now let me ask the question on this last one. This is what I wanted to come back to. What do you get if you add 64 to 192? Let's do it. 192 plus 64 equals 6. 5, carry the 1, that'd be 2. Whoa, buddy. Hey, wait a sec. So you're saying if we keep going with this increment, we're going to get to 10.0.256.0? No, that's broken. We can't do that. Well, if you hit that point, don't worry. You haven't done anything wrong. That just tells you you've reached the end of an octet. So hang on, before we do anything more, let's fill in what would the last IP address for this range be? It'd be 10.0. Let's subtract 1 from 256. 255.255. Just I should erase this and write the whole thing just so it looks nice and consistent. So this goes through 10.0.191.255, right? So going with this goes 255.255 right there. So what that tells you is you've reached the end. Now, wait a second. The end? What do you mean? We were after 1,000 networks and we only got 4, right? How do we get 1,000 networks when we're at the end right there? Well, we're at the end of our first kind of major octet. We're at the end of the zeros. So again, think of that bizarro math world. If I said +1, it'd say this, and I said, okay, what's the next IP address after that? Well, 256 would zero out, carry the 1. So this would zero out, carry the 1, and we move over to 10.1. You see where we're going here? So there really is no 10.0.256. Oh, I can't do that. There's no 10.0.256.0. The next one will actually go to 10.1.0.0. That's our next IP address. And then we start the whole thing all over again. 10.1.64, 10.1.128, just kind of keep going down with that counting. And once you see the scheme of how this works, and I'm squeezing at the bottom, 10.1.128.0, you see the scheme. It just, and now you start looking. Oh, that's how we get 1,000 networks. Every single one of these octets, all the way up to 255, gets 4 networks apiece. That makes sense, to where now I can see where that fits in. So this just kind of repeats itself. That's why I wanted to do this example. You might say, well, we've already seen kind of a class B. Well, I wanted to show you again, breaking that paradigm a little bit more to see. All of that's possible. Now, there's always 2 levels of learning. There's one where you can watch somebody who's explaining it, like me, and go, okay, I get it. I kind of see what you're doing. I see what you're following. And that's a major milestone. Congratulations if you're at that point. If you're not at that point, then rewind, go back through it again, and just keep watching it until you're like, that it's starting to click. It makes sense. But there's a second level of learning that you absolutely need to reach with every concept in the Cisco world, but especially this one, and that is the level of doing it yourself. So right now I want to transfer you from level 1 to level 2 by giving you this homework assignment. You can see all it is. I put the class of network that is. So this is a Class C network, Class B network, Class A network. So I've got 4 examples for you to work through, and to check your work, I'm going to include a supplemental file with this nugget. You can actually download it. I think the supplements are all included in one big zip file, but you can download it so you're able to check the work. And I'm going to write this file in such a way that it's kind of step by step. It's broken down as if I was explaining. It's the best I can do in writing style to explain what I'm doing as I go through each one of them. So right now, before it seeps out of your mind, sit down with a piece of paper and see if you can work through these. Try not to look at the answer, because these are the 4 examples that I'm giving you. Try not to look at them. Go back through the lecture and see if you can kind of piece together the steps and get through them all yourself, and then check your work. Also realize that there are literally thousands of free examples of subnetting questions out there on the internet. The world knows that this is a hard topic to get. So you will find, if you just go on Google and type in subnetting examples, you will find site after site after site that gives you practice problems and so on that you're able to work through and check your work. Well, that leads us to the end of Subnetting Style 1, which is creating subnets based on network requirements. As we move into the next nugget, we'll start expanding on different styles of subnetting, different styles of examples. But for now, I hope this has been informative for you, and I'd like to thank you for viewing.